Okay, we're continuing in our discussion of operational amplifier applications, and we're going to be looking at the subject of active filters. And active filters could be differentiated from what we would call a passive filter. A passive filter is going to be a filter that's based on resistors, capacitors, inductors, and there will be no, a passive filter doesn't have any voltage or any amplification, whereas an active filter, we're going to use additional voltage and additional or amplification to cause a more precise filtering. Now, passive filters can be quite accurate, but they do not amplify the signal at all, and they do not use, and they just simply take the frequency that's sent in and filter it and provide an output. Oftentimes the output will be quite severely attenuated. In active filters there's an amplifier involved, so the signal can be boosted in the process. Okay, there are four types of filters. First of all, there are low-pass filters. They pass only the low frequency signals, and these are used, as one example, they're used in DSL lines. High-pass filters, they pass only the high frequencies. Band-pass active filters, they pass only a specific band of frequencies. You might see something kind of like that, and they're used in radio and TV transmissions. Band-reject filters, they chop out a specific frequency. You might have a band of frequency where suddenly a certain band of frequencies is just cut out. They're used to filter out 60 hertz hums. Sometimes they're used in some cable systems. They'll use these to block certain channels. First one we're going to look at is the low-pass filter. And what we have here is a graph of the output of a low-pass filter, and so you get the idea of what's going on here. Here we have a frequency going from 0 up to whatever frequency that we're filtering, and here is the amplitude of the signal. And what we have here is in this band here, we're passing everything, but when we get up to a certain frequency, we begin to lose the signal. And there's lots of different types of low-pass filters, but this is one of the common configurations that will give us low-pass filtering. The frequency of concern is called the critical frequency, and the critical frequency on this graph is this point right here, and we call that the point where the signal is prior to this point. We're going to pass this signal. At this point, we're going to begin to severely attenuate that signal. And the formula is 1 over 2 pi r times the square root, and I guess I could draw this out, times the square root of C1 times C2. And this is the actual calculation using the values that we have here. And if you do that, you'll find that the frequency is 7.04 kHz. At the critical frequency, the output will be 70.7% of the input voltage. Now, this value isn't in your text, but from this graph that is in your text, you can kind of ascertain that that is actually the value. The reactance of the two capacitors is such that they look like an open for frequencies below 7.04 kHz. Above 7 kHz they short, and the input does not get to the output. So if you look at the position of the capacitors in this circuit, one is right here at the input, and then one is in the feedback loop. Now, as we apply a signal here, at low frequencies they will both have a high reactance and they won't be passing a signal. And so this input in this case will get to the op amp, it will amplify. This will be a resistance in parallel with this, so there will be a feedback loop, and we will have the passing of a signal over here. Now, when this gets to a sufficiently high frequency, in this case of 7K, these capacitors will begin to conduct. They'll begin to look like a short, and this signal, instead of getting the op amp, it's going to have an alternate path to ground, so it won't be conducting or won't be getting much passage of signal. And this capacitor will begin to short, so the feedback loop will begin to look like a straight short, and so there won't be much amplification there. So what we'll end up with is that in the low band of frequencies it will pass, as soon as it gets up to the critical frequency, we will begin to lose and it will be severely attenuated. And this is an example of a low-pass filter. Some of you may have seen these. If you're using a DSL line, you would plug this into your telephone, and then you know when you're using your phone here, this will eliminate some of that potential high-frequency noise in the DSL line. DSL lines send data and voice over the same line. The high-frequency data is in the range of 25 to 1.5 megahertz. The voice data is below 4 kHz. Low-pass filters are used prior to the phone to reject the high-frequency data so the user hears only the voice. So if we look at a graph here, we'd find that going up to 1.5 meg possibly, then this would pass only those frequencies that are below 4K where the voice data is. And this stuff up here, which would potentially generate a lot of noise, is rejected. Then this is a high-pass filter, and what we'll note here is the high-pass filtering is accomplished by swapping the positions of the resistors and capacitors. And so that low-pass filters, we had resistors here and we had capacitors here. And so just by simply changing positions of those components, we can build a high-pass filter. In this case, the capacitors look like an open until the input frequency approaches the critical frequency, and the formula is 1 over 2 pi times the capacitance times the square root of R1 times R2. And in this case, what we're going to have is just the opposite of the low pass. In the low frequencies, we're not going to pass anything until we get to the critical frequency, and then we're going to begin to pass everything. And this would indicate the high frequency range. So everything above a certain frequency will be passed. And the idea here, and it's fairly straightforward, is here we have a signal coming in. The reactance of these capacitors is going to be such that at lower frequencies they're going to look open, and it's not going to pass anything until it gets to the critical frequencies. Then these capacitors will begin to conduct, and then we will pass a frequency. And then the higher the frequency is, the capacitors are just going to conduct, and they're going to pass everything above a certain frequency. And so you have this characteristic curve of a high pass frequency. Now here, this is a simulation from your multi-sim package, and this is a high-pass filter. So let's look at this. Let's see, why don't we start, we'll look at the calculation of what frequencies are actually being passed. So here we have the critical frequency formula, and if we plugged in these numbers, and the numbers we're going to be using here, there's the 0.05 microfarad capacitor, and the 11K and the 22K ohm resistors. And if we plug those into this formula, I'm draw a little line there just to make sure that square root goes across that whole those two items, we would get about 205 hertz. So what this is saying is that this filter will block those frequencies below 205, and then it'll pass everything above that. And this filter is available in your multi-sim package. Now let's look specifically at the circuit and see what we have here. Here we have the op-amp. Pin 4 goes to the negative, pin 7 goes to the positive, and then we have the two capacitors and the two resistors. Now we also have a device called a Bode plotter connected to this, and a Bode plotter is a very interesting instrument. What it does is, and as the user, you go in and you plug in the values that you want to use, and what we're looking at horizontally, we're looking at a frequency range, and this is the initial frequency and this is the final frequency. And so the initial frequency we're starting at is way down at 100 millihertz, and the final frequency is 10 kHz. So we're looking at a frequency from close to 0 to 10 kHz. And what we see here is the relative amplitude of that signal. Up here, we're going to be at a amplitude probably about 0 dB actually. And then below this, we're going to experience signal attenuation. And you can see I have stopped this simulation at this point, and you see this blue line, and you'll notice that the blue line, we're down 3 dB. Actually, that is the 70.7% value, and we're at a frequency of 204 hertz, and you'll note that our calculated value was 205. But this is an excellent tool to assist you in looking at the output of filters. Remember, going horizontally here, we're looking at frequency, and going vertically, you can adjust for the actual amplitude of the signal, and it is actually in decibels over here. Okay, so the Bode plot, when you use this guy, you would connect the Bode plot, the input and output of the Bode plotter. One would go to the input, and then the other would go to the output, and then of course the negative and the negative here are both going to ground. But this will allow you to view what would this device produce over a range of frequencies. And like I say, as a user, you can go in and you could put this up to 1 megahertz if you wanted to, but then it would just kind of go right up here, and then it would be across. By making it more specific here, we're able to really tune into that specific frequency. Okay, in filters here, we have looked at this high-pass filter. And we looked at a little bit about the theory, and then we looked at the low-pass filter. We looked at an example of a low-pass filter, which is a DSL filter. And again, we looked at theory about low-pass, and then we just introduced the subject of active filters. And in the next section, we're going to look at the band pass and the band reject.